This, however, is Sagittarius. And in fact, work done as well. I mean, there's been a lot of study on Sagittarius. Paul Harding and others at CASE have been doing a lot of work from SDSS. There's also other groups, Majewski and people, who have been looking at the sky with other large-scale surveys. And they find actually not only is there the center of Sagittarius, but this is a horrible projection of trying to, plot the entire curved sky on a flat piece of paper. So this is what you see. The most important point is just you'll see this big loop going through the data. Just going there and repeat it on the other side. That is a stellar stream, a stream of stars that's been pulled from Sagittarius. Because what we think is happening is this. As a small galaxy, such as Sagittarius, it orbits around the Milky Way. Okay? It orbits around just like anything orbits, like the moon orbits the Earth orbits the sun orbits around the galaxy, and so on. So small galaxies can orbit around bigger galaxies. But for the same reason that we have tides, because of the tidal effect of gravity, such that the near side of the Earth, relative to the moon, the side of the Earth that's nearer to the moon feels more gravity from the moon than the faraway side. So that produces a swell in the oceans as the Earth tries to stretch out in that direction. That's why we have tides. That is why Sagittarius is being pulled apart. Because the near side, at any point, the near side of that galaxy relative to the center of the Milky Way is feeling more pull, is feeling more gravity than the other side. And because it's going around and around, it produces the effect that stars want to pull out in that direction, and then sort of, they've moved on a little bit since then, and you produce this beautiful tidal, what we call a tidal stream, a stream of stars produced because of the tidal effect of gravity. Okay, so that's what we believe is happening to Sagittarius, is being pulled apart. In some ways, you could think of it as being cannibalized or digested by the Milky Way, because those stars, as they're being pulled out, where do they go? They become part of the Milky Way galaxy. Okay, so this is actually how a galaxy like the Milky Way grows, by actually eating up smaller galaxies in some respects. This is now a well-known phenomenon. This is a galaxy called the Splinter Galaxy that I was unfamiliar with prior to seeing this beautiful image. It's an edge-on galaxy, but this is what sort of, as the typical image that is shown. Then an amateur astronomer, actually, a very rich amateur astronomer with his own robotic giant telescope, it should be said, but an amateur astronomer nonetheless, did a very, 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 very long exposure photograph on this galaxy. And this is what you see. And you'll notice immediately this beautiful, large sweeping arms that looks awfully like those streams of stars that I was just telling you about. This galaxy is far enough away that you're not seeing the individual stars, you're just seeing the net light from all of them. But, again, this is the sort of things, and we see this again and again, and we believe it's the result of small galaxies being pulled apart as they orbit bigger galaxies. Now, this is where things get cosmological. Insofar as the picture that we now have, and it's fueled in part by some of the discoveries that I was just telling you about, the fact that dwarf galaxies have lots of dark matter in them, for example. The fact that something like Sagittarius is actually being cannibalized, being pulled apart by the Milky Way. There's now a picture that's emerged predominantly stimulated by studies of faraway galaxies, by things like the map of all of the galaxies that I showed you from SDSS at the start, all of those filaments and clusters and such like. So primarily fueled by studies of the much more distant universe and trying to understand very large, faraway phenomena. We now have a picture of how we think structure is forming in our universe. Essentially, the idea is that at early times, you don't have much structure. Instead, what you have is a relatively smooth sea, if you like, of mass. And most of that mass is, in fact, dark matter. Okay, that makes some people uncomfortable. And it's not surprising, maybe. But most of the mass in the universe is from dark matter. So essentially, what you have is a smooth distribution of dark matter. But it's not perfectly smooth. There's deviations away from smoothness. In fact, this is actually something we can observe in what's called the cosmic microwave background. But again, I won't go into that, other than to say that it's never going to be perfectly smooth. So if one of those little bits is a bit more massive, just one of those parts just happens to be a tiny little bit more massive, then over time, remember, it's a bit more massive, it feels more gravity. Because it feels more gravity, it pulls a bit more mass towards it. So it grows slightly more massive. And it continues to do this, and so on and so on, and then eventually it all runs away, and things just start growing out of where you had nothing before, exactly like what's going on in the simulation here. So if you have effectively a smooth distribution of mass, but just slightly imperfect, and then just let gravity do its thing, this is the sort of thing that happens. You can see that little blobs form. We call these blobs halos. These little halos merge with other little halos to form a slightly bigger halo. Meanwhile, another halo is growing really big through that process and pulling towards lots of other little halos. Then those two bigger halos that formed are actually now merging together to grow an even bigger halo, and so on and so on and so on and so on. Okay? In other words, from a very smooth distribution of matter, just because of gravity, you can get something like this. And if you think back to what a galaxy cluster looked like, with lots of blobs all surrounding it, then you can see that there's qualitative similarities. And in fact, the agreement is much better than just qualitatively. When you look in detail, there's very good agreement. The same thing happens, though. This is effectively exactly the same. It's just these are cool movies, so I thought I would stick two in. Except this is actually now, the previous one was trying to reproduce something that looks like a cluster of galaxies. This is trying to reproduce the Milky Way galaxy. You'll notice immediately it doesn't look anything like the Milky Way details, which we'll come back to in a second. But firstly, the thing in the previous image, the thing in the previous movie and this look more or less the same. Okay, generally what's going on. And that's because, again, even though this is a galaxy and the other one was supposed to be a cluster of galaxies, gravity doesn't care what size of things you are. It just operates the same on all sizes. So you just kind of scale everything up or down. The overall effect is the same. The idea now in a sort of modern picture of how structure forms and consequently how does the dark matter and galaxies form, this is what we should be able to see something like if we could see dark matter, which we can't by definition. So what can we say? We can immediately say that from going to dark matter, from going to stuff that we can actually see, there has to be some serious things going on. Because quite frankly, when I showed you the simulation of the fly-through of the local group, you probably didn't see tens of thousands of little dwarf galaxies surrounding the Milky Way, because there wasn't. Okay, there was about 30. There may be as many as a couple of hundred that we still haven't found, but there's not tens of thousands of little blobs surrounding the Milky Way that we can see. So if they're there, it means we can't see them. Okay, and the idea, remember, is inside blobs, galaxies form. So what it must mean is that inside some of the smallest blobs, galaxies do not form. And this is a huge area of research now because nobody actually understands really how can we make this work. And it's not because we think there's something fundamentally wrong. There may, of course, always be. Rather, it's because the complexity of having to deal with all of the different types of physics, the interactions that are going on when you're dealing with gas forming into stars, which then blow up in what supernova explosions. These supernova explosions then heat up some of the gas, and then you have other gas which is trying to cool through molecular mechanisms, blah, 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 blah. It's an incredibly complex thing to simulate. Okay, so we're not there yet. Instead, there's another approach we can take, which is sort of a way of educating ourselves. It's not a way of making a breakthrough, but it's a way of trying to understand in what direction we need to go to ultimately understand how to make this work, if indeed we can make this work. And that is to say, well, we have something like this, but we know more or less what the Milky Way looks like. So what do we have to do to make it work? And when you do that, this is the same kind of movie where all of that same dark matter stuff is going on, but now you're not looking at the dark matter. Now you're just looking at galaxies. So all of those little blobs falling in are dwarf galaxies falling into the Milky Way. Okay, and the things that actually the colored blobs represent are stars. So in other words, this is what we think should be going on with the stars in the outer reaches of our galaxy. If that whole idea of how we think structure forms, and remember that works very, very well on larger scales, if that idea is right, then in order to sort of reconcile that idea with what the predictions are on the galaxy scales with what we see, something like this should be going on. In other words, when you look out into the Milky Way, you shouldn't just see Sagittarius being eaten by a galaxy. You should see a whole load of ones. You should see a whole load of dwarf galaxies, like we do see in the outskirts, but you should see some which have been completely pulled apart. The stars are spread all over the place. You should see some which are in big stellar streams. You should see others which are partly in between, and so on and so on. Okay? In other words, you can see now that this isn't necessarily a very strong prediction, but it's what needs to be there. If that's not there, then our model for how this galaxy is forming is definitely wrong. That is there is not going to prove that it's definitely right, but that is obviously not obviously wrong at this point. And at the moment, that's really where we are in this field, because the physical understanding, we know some of the processes which we think are important, but trying to pull all of those together is an incredibly complex thing to do. So is that what we see? I told you, obviously, in 1994, we found Sagittarius, or Rodrigo Abata found Sagittarius. But what else do we see? Well, again, with the Sloan Digital Sky Survey, they've done a fantastic job of mapping what our galaxy looks like in stars over a very large area of sky. Okay, and remember, if our general idea of how things form in the universe is right, what they should see should be a big mess of dwarf galaxy streams, blobs, everything like that. And that's essentially just what I'm saying. And remember, by seeing this, we start educating ourselves on, well, did we get that right? Well, no, we didn't. Well, okay, well, is it possible to get it right by doing this? No, it's not. Oh, then we need to change something more basic. You can see how it's kind of an educational process where we have to go backwards and forwards. But this is the general idea. When you look, this is amazing, really. This is what the map of stars looks like. Just a map of stars across the sky over the fraction of sky that the Sloan Digital Sky Survey, a quarter of the sky was looked at. And this is what you see. The number one, almost the only thing you need to take away from this is that it's not smooth, okay? If it was smooth and everything in the outskirts was just lovely and rosy and there was nothing going on, just stars would be evenly distributed. Wherever you saw, you'd see the same number of stars. You wouldn't see any structures, you wouldn't see any streams, you wouldn't see any blobs, but you do. And so this is very good. We see Sagittarius, the stream from Sagittarius, which is highlighted there. You may see the text. We also see another stream. You'll notice it's kind of like seems to split into two as you're looking at it. Whether it actually does split into two or whether it's two separate streams, we don't know. But clearly there's a lot going on there. You'll also notice other very thin features like the orphan stream. This thing here. And another big blob here, this big blue blob, which is called the Monoceros stream. The orphan stream is called the orphan stream because we don't know what produced it, and so it doesn't have a parent, and so it's very sad. And I know, it's an emotionally crying game, astrophysics, really. Anyway, and then you'll also see there's other sort of much more coherent blobs marked. Those blobs are some of the dwarf galaxies, and these are some of the super, super, super faint dwarf galaxies. Before I was talking about Ursa Minor and how it's star matter dominated, but then I showed a graph where there were things even fainter, up at 1,000 times more mass than they should. That's these things. These things are absolutely ridiculously faint. These images are not even proper images. They're what you might call press release images to actually bring out the feature, because otherwise you can't see it very well, because it's only there by actually counting stars and you see there's an overdensity. To give you an idea of how faint some of these galaxies, not all, but some of these galaxies are, eventually the sun will evolve into what's called a red giant. Okay, that's part of what a sort of average type star like the sun does. When it does that, the total light it gives off will be much more. In fact, it will be more light given off by that one red giant branch star than the entirety of some of these galaxies. Because some of these galaxies, just by coincidence, don't actually happen to have any giant stars in them, just because of the stage we're looking at them. And the total amount of light in them, the total amount of stars in them, is equivalent to just 500 of our suns. Remember, our galaxy has 100 billion stars in them. Some of these things have 500 stars in them. The fact that they exist at all is perhaps the most interesting and exciting thing to take away from the study of these objects, because these are hard things to understand. And it's only, again, by looking in the outskirts, like SDSS does, that we can see these things. This is some of the stuff which I've been doing. This is around the Andromeda galaxy. There you can see Andromeda, there you can see Triangulum. Also, over on the left, as you look at it, I placed a picture of the full moon. The full moon is not actually always there, okay, in the same position relative. It's for scale, okay? But you can see that even the main body of Andromeda, as people think about it,